Okay, so now let's look at climate as one of the processes that aids in the rate of weathering. So climate factors, particularly temperature and moisture, are crucial to the rate of rock weathering. For example, the frequency of the freeze-thaw cycles greatly affects the amount of frost wedging that there is, and freeze-thaw cycles are affected by the temperature. The amount of root wedging, for example, has to do with both temperature and moisture because plants need a certain amount of both to fracture the soils and rocks. So climate affects physical processes, right? But also both temperature and moisture have a large effect on the rates of chemical weathering. And they will also determine the kind and the amount of vegetation that will be present at an area. So for example, areas that are lush in vegetation are typically found where there is a thick mantle of soil rich in decayed matter in the area that exists. In turn, the thick soil mantle and to a point the decayed matter that exists in that soil are there thanks to the chemically active fluids such as the carbonic acid and other organic acids in those regions. So the optimum environment for chemical weathering is usually a combination of warm temperatures and abundant moisture. So in polar regions, chemical weathering is almost ineffective because frigid temperatures keep the available moisture locked up, as ice, obviously. Whereas in arid regions, for example, although there might be enough temperature, there might be enough heat, there is insufficient moisture to promote any rapid chemical weathering. So areas that are both moist and warm tend to be where most chemical weathering occurs. So something like the rainforests in the tropical regions are the best. Areas such as the Pacific Northwest are relatively good, but not great because it still gets somewhat cool. So I hope that's making sense. All right, so now we'll look at differential weathering. So these masses of rocks usually do not weather uniformly. For example, look at Shiprock in New Mexico, which is the bottom right picture. This gigantic rock protrudes over the rest of the surrounding environment. When there is this differentiation in the weathering rates in different rock types and rock features, that is what we call differential weathering. So most resistant rock types will stand out as ridges or pinnacles or as steep cliffs, as you're seeing in all the pictures that I have above. The different formations angles will also have an effect on the weathering, meaning at steep angles, so if the rock is at a steep angle, it has a steep angle, it is hard for water to puddle at that angle, and so it won't reside very long, so it won't weather it very long. But the main effect on differential weathering has to do with the rock type. So although angles do help, weather or not weather, the main effect will come from the rock type that you have. Having, for example, intrusive igneous rocks weather relatively slowly compared to some sedimentary rocks. Okay, so here is an extra credit opportunity that I have for you all. And you'll only see it if you watch this lecture because this slide will not be part of the slides that are on the slide link on Blackboard. So I would encourage you all to do this extra credit. It's an easy way for you to get some extra points. And then once you do it, bring it to class the next time. It's not very hard, as you can sort of tell from the questions. It has 5 questions and they're relatively easy. It shouldn't take you more than 10 or 15 minutes tops. All right, so weathering is a key process in the formation of soil. Along with air and water, soil is one of our most indispensable resources. So also, just like air and water, if you would, it tends to be just taken for granted. Many times we don't realize of what the importance is and how we have to care for it. So soil itself is the interface between the living and the inanimate world, okay? All of life owes its existence to about 12 different elements or so, which ultimately come from the Earth's crust. And after weathering has occurred and grains have been eroded, plants do the intermediary role of extracting the needed nutrients from the soil, from the inorganic particles of the soil and the air, and provide them to the animals that reside on Earth, including humans. So when we view Earth as a system, like we did in chapter 1, for example, we had different spheres within this system. Soil is considered an interface of all of these spheres, a common boundary where the different parts of the system actually interact. So if you think about it, soil forms where atmosphere, geosphere, hydrosphere, and biosphere all meet and interact. Soil is also very dynamic and sensitive as well to almost every aspect of its surroundings, which makes that when there is any change to the environment around, and such as for example climate or vegetation cover or animal activity, then the soil is going to respond in one way or another because it's very sensitive and changing. But eventually, hopefully, this will achieve some sort of balance. It likes to stay balanced, although it does react easily to changes. Okay? Okay, so most of Earth is covered by regolith. Regolith is a layer of rock and mineral fragments that are produced by weathering. Soil itself is a combination of mineral and organic matter, as well as water and air. Okay? The overall concentrations of these four things may vary from place to place, but there are always these four things regardless of the place. The image in the slide that you're seeing down there shows the average of those four components by volume in all of the soils. So nearly half of the soils is made up from inorganic weathering materials, and then 5% is made out of humus, which is the decayed material from animals, plants, and from living organisms. The remaining half of the soil is made up of empty space, through which both air and water circulate. So that empty space, about half the times is filled with water, half the times is filled with air. Or not half the times, but half of it is filled with water and half of it is filled with air. Okay, so although the mineral portion of the soil pie chart as you're seeing is much greater than the humus portion, humus is very key to soils for a few reasons. One is that it enhances the soil's ability to retain the water, aside from being also very important of a source of nutrients to plants. Air and water are very key for living organisms who dwell in the soils and take advantage of the soils. So almost all of the land-based animals really are benefited by both of these things. As I have sort of implied before, the water that's in the soils and in the pores of the rocks is far from pure, meaning far from being just H2O, but rather it tends to carry a lot of ions, which make the soluble nutrients which plants use as they grow on the soils, which are full of water, of these ionized water. And then the pore spaces where the air resides have the necessary oxygen and carbon dioxide for most of the microorganisms and plants that live in that soil. So all of the parts from the soil are very important for the functioning of the soil as it is. All right, so soil grows from top and from the bottom. Organic matter above usually, and weathered stuff coming both from the bottom and from the top, right? So sometimes you can have weathered material come from the bottom, and then sometimes you can have the weathered material be deposited from sources on the top. Soil itself is the product of a complex interplay of several factors, including those factors that are listed there. So we'll look at all of these in detail. We'll look at parent material, climate, plants and animals, time, and topography. And although we're going to cover each of these controls independently in the slides, they act as interdependent. So they act together towards controlling the soil formation, okay? But we'll cover them one by one in the slides. All right, so the first control on soil formation that we'll look at is parent material. So parent material is the source of weathered material. This weathered material undergoes physical and chemical changes as the soil formation progresses. The parent material can be the soil's underlying bedrock, or it can be a layer of unconsolidated deposits from far away that have been carried from far away. So if the parent material is the bedrock underneath, the soils are termed to be residual soils, so something that resides. By contrast, those soils developed on the unconsolidated sediment that came from far away are called transported soils. So the soils for this scenario form in place and they form on parent materials that have been carried from elsewhere and deposited by gravity, by water, by wind, or by ice, or a combination of all of these. So parent material will influence the soils in two different ways. The first way in which it influences it is through influencing the rate of weathering and thus the rate of soil formation. For example, transported soils usually develop faster than residual soils, and this is because the unconsolidated material is already partly weathered, right? Because it had to be weathered away in order to get to its new location, to be deposited in its new location. So it's already somewhat weathered, and it can continue to be weathered, but it's already partly weathered. The second way in which parent material will influence the soils is on the soil's fertility. So the chemical makeup of the parent material will affect the soil's fertility, and thus the vegetation which that soil can support. So for example, I think many of you have heard that volcanic material tends to make very fertile soils. And this is true. Some other soils that are more iron rich are not as fertile. So it depends what type of parent material you have, or no, it depends, but it gives a lot of weight to the fertility of the soils, the chemical composition from the unconsolidated inorganic material that the soil contains. Okay, for a second control on soil formation, we have climate. So climate is now considered to be the most influential control in soil formation. Temperature and precipitation are the elements that exert the strongest impact on the soil formation. As examples, a wet and hot climate will produce a thick layer of chemically weathered soil, at the same time that a cold and dry climate produces a very thin mantle of mostly mechanical weather debris. So also the amount of precipitation will affect how fast materials are carried away by the percolation of water. So again, water will flow through the soils and carry away some of the materials. This process is called leaching, as we will see later in the soil profile. Overall, this leaching will affect the soil's fertility as well, because some of those ions that are useful nutrients will be removed from the system faster. So finally, the temperature and the precipitation, again, control in terms of life activity will also have an impact on soil. So if the temperature is pleasant for life activity to take place, that will also have an effect on both weathering rates and also on the amount of organic material that the soil has. Same for plant activity. If the temperatures are suitable for more vegetation, then the amount of organic material will increase, and the different acids that are produced will also increase. And so we'll look at that in the next slide.